Hello class. In this video, we're going to talk about lesson 8.4, the z-test for a proportion. So the essential question is, what is the specific statistical process for testing hypotheses involving proportions? So our learning goals for today are to be able to calculate a test statistic for proportions, find critical values, find rejection regions, and use a z-test to test a population proportion. So there are no new vocab for this lesson. It's going to be based off of the previous vocab. But we will look at proportions today. So essentially, in the previous lessons, we talked about using z-tests and t-tests. So so we looked at a couple of tests for the mean, which was the z-test for the mean and the t-test for the mean. Now, the z-test for the mean, recall that it could be used when the sample size is large enough or the population is normally distributed and the sigma was known, the population standard deviation. If you knew either one of those things, then you can go ahead and proceed with the z-test for the mean. However, if your sample size was small enough and you did not know the population standard deviation, then you needed to proceed to use the t-test for the mean. And that's used when the sample size is small and sigma is unknown. And then the t-distribution we mentioned in the previous lesson is essentially a family of curves that resembles the z-distribution, having that characteristic symmetric shape, symmetric nature, but the type of curve that you use depended on your degrees of freedom. And we calculated that by taking the sample size, taking a -1. So remember that the z-distribution is only one curve, and that's the standardized normal distribution, whereas the t-distribution is a family of curves. All right, so that's what we did over the past few lessons. Now, in this lesson, we're focusing on proportions rather than means. So a mean is an average, whereas a proportion is simply, a percentage, right? Or it can be expressed as a fraction or a decimal. So when do we actually use this? Well, actually, there are a lot of times in which we actually have to test a claim about a population proportion. So for instance, when we're looking at percentages, for example, of car accidents or anything like that that's factual that you see in an article. For example, an estimated 52% of car accidents happen within 5 miles of a person's home. In that case, that would be, a statistic that you would normally think of. In fact, we actually see a lot of claims that use percentages in them. So this is not actually surprising that we have to figure out how to how to actually address these claims. So you can use the z-tests for these proportions as long as the following conditions are met. So remember that with a proportion, we're going to think of it as either success or failure. So in the case of the car accidents, you would go ahead and do your study, right? You would take your sample of, you would randomize your sample so that you select a certain amount of people or a certain amount of drivers that are within five miles, right, of their place. Let's say within 5 miles of a certain geographic location. And then you would say, okay, you would tally those ones that do have an accident within that range, right? And you tally the ones that don't have an accident within that range. So this is success or failure. They either meet that condition or they do not meet that condition. So that means that you're using a binomial experiment. So therefore, we can think of this as a binomial experiment in which the conditions are met. Okay, so we have to meet the conditions of a typical binomial experiment. We talked about this in chapter 5, I believe. It was in the probability unit, so it might have been chapter 4. But a binomial experiment, remember, is two categories, success or failure. And then some of the conditions include, the trials have to be independent from one another. The probability of success has to be the same in each trial, and so on and so forth. So those conditions have to be met, and the sample size has to be large enough. So that means, in this case of large enough, we know that large enough for the z-test is greater than or equal to 30. Now, large enough for the z-test for the proportion is that the sample size times the proportion or probability of success, that's what we call little p, probability of success, or the proportion, population proportion, So the sample size times that has to be greater than or equal to 5. And the same thing for n times q. Remember that this is the q is the probability of failure. So if, for example, 40% success, then that means q is going to be 60% for failure. You multiply that by the sample size that you took, and that should also be greater than or equal to 5. Both of them have to be met for you to proceed with the test. All right. So if the conditions are met, you can go ahead and perform a z-test. Now, the formula for the test statistic for the z-test is actually given below. So that's the formula for the z-test. So in this example with this formula, the p-hat is actually the sample proportion. The p is the population proportion, which we also call the probability of success. The q is the probability of failure, which is the opposite of the probability of success. We call that the complement. In this case, so if 40% was success, as I said earlier, then 1 minus 0.40 or 0.60, same thing as 60%, is a probability of failure. And then the n is the sample size, the typical sample size. Now, to calculate the p-hat, you're going to take the number of successes, which we call x, and divide it by the sample size. And so it's a pretty easy calculation to do. All right, so let's look at an example of verifying whether the normal sampling distribution can be used to test a claim about a population proportion. So basically, can we use the z-test for claims about a population proportion given the following conditions? So for the first one, we have that the p is 27.8%, so 0.278, and the sample size is 110. So all you got to do is, assuming that the binomial conditions are met, let's see if the sample size conditions are met. So we're going to do n times p. Remember, n times p has to be greater than or equal to 5. So that means we're simply going to multiply the 0.278 times 110. And then we're going to see if that's actually going to be greater than or equal to 5. So let's do that on the calculator real quick. So you're going to get 30.58. Which is indeed greater than or equal to 5. So far, so good. And then we're going to do n times q. Remember that q is simply, and of course I wrote this in the wrong order, but it doesn't really matter when you're multiplying. But I'll just switch those so that you know that n is 110. So n is 110 times, and then to find q, you're going to do 1 minus p. So 1 minus 0.278. And then we'll get that number here. So you're going to get 79.42. And this is greater than or equal to 5. So this checks out, which means that yes, you can actually use the z-test. Okay, so proceed with you. So we'll say yes, use the z-test for the proportion. All right. Now we're going to do part B now, same deal. So we're going to do 18 times 0.79, and we're going to see if that's greater than or equal to 5. So that's 14.22, which is indeed greater than or equal to 5. So that checks out. And then the last one, 18 times 1 minus 0.79. 1 minus 0.79 is 0.21. All right, and that's going to give you, that should give you about 3.78. Double check that real quick. Yeah, so 3.78. And if you notice, this is actually not greater than or equal to 5, right? So this means that one of the conditions have not been met, so you cannot proceed with the z-test here. You won't be able to use the z-test or normal sampling distribution for this. So no. All right. So pretty straightforward. So now the steps to perform a z-test for proportion are very similar as we've seen in the previous lessons, okay? So the only difference really being the fact that you don't really have to do a degree of freedom like we did with the t-test because it is a z-test after all. And the basically the only difference is in the calculation of the test statistic, the formula. So first step is still going to be write your claim. Second step is still going to be identify your alpha, your level of significance. Then you're going to, identify your test direction, sketch your distribution, all of that stuff. So finding your critical value, that's going to be the same. Shade the rejection region, and then this is the next step that is different is that you're going to be using that new formula. Then the rest is the same, making the decision and drawing a conclusion in the context of your claim. So those steps are the same. So let's look at an example of using the steps. So the AMA conducted research in 2017 and found that at least 24% of US adults are smokers. A random sample of 300 US adults were surveyed and 20% said they currently smoke. Is there enough evidence to reject the AMA's claim at a 1% level of significance? All right, so they do give us the claim. They actually tell us directly what the claim is. So the claim So according to this, the claim was that the AMA's claim that at least 24% of U.S. adults are smokers. So in this case, remember proportion. When you see a percentage, you think proportion. When you think proportion, you're going to think population proportion, which is P. Okay, so we're not going to use mu anymore. Mu was for the population average, right? The population mean. This time we're concerned with proportions. So the P is going to be greater than or equal to, and then you're going to convert this to a decimal, so 0.24. Again, we prefer to use decimals when we're using the hypothesis test, although it doesn't really matter. All right, so H0. So right now, this is a statement of equality because it has the equal sign, the greater than or equal to. So therefore, it belongs to the null hypothesis. So we're going to say P is greater than or equal to 0.24. So that our claim belongs there. And then we're going to do the opposite of that. So it's going to be less than. And because it's less than, that means that it indicates that since the H1 is less than, it indicates it's a left-tailed test. All right, now the alpha, they tell us what the alpha is. That's 1%, so 0.01. All right, so now what we're going to do is we're going to find our critical values, and for that we need to use our we need to use the z-distribution table. So since this is a left-tailed test, we know that we're going to have a negative critical value when we do this. Okay, so and since it is a left-tailed test, we need to figure out what the area is going to be on the left side. So remember that the area for a left-tailed test is simply your alpha, which in this case is 0.01. All right, so we're going to look for 0.01 on the z-chart or 0.0100 to see if we get a z value that is closest to that. All right, so on the right side, I went ahead and provided you with the table as usual, the typical z distribution table, and we're looking for an area of approximately 0.0100. So if you look at your table, at the table in front, we have the closest thing to 0.0100 is this guy here, 0.0099. And then if you trace backwards to the column and row, then you see negative 2.3 there. You go back up the column, and that's going to be 0.03. So our z-score, our critical value is negative 2.33. And this makes sense since it should be negative since it's on the left side. All right, so we're going to go ahead and proceed to label that here. So that's about there, negative 2.33. We're going to shade our rejection region, which is step 5. All right, so now we got our values and we shaded our region. So our test statistic, remember, is calculated by p hat minus p divided by the square root of pq over n. So we're going to go ahead and calculate that now. So we need to figure out what the p hat is, and we'll do that over here. I'm not sure if they actually told us outright. We might have to actually calculate it. No, they did actually tell us. So sometimes you're going to have to calculate the p hat. Here they said a random sample was taken of 300 adults, so that's my n. N is 300. This is our p, which is from our claim, and then this is our p hat. P hat is from our sample. So from the sample, they said that it was 20% that currently smoke. So, and then of course, obviously that's our alpha. Now, sometimes they won't actually tell you the p hat. Sometimes they'll tell you the information. They'll say you took a random sample of 300 adults, and out of the 300 adults, let's say 100 said that they currently smoke. Now, if they said 100 currently smoke, then the p hat would be 100 divided by 300. Okay, in this case, smokers are considered success because we're interested in the smokers. So whatever you're interested in, that's considered success. So if 100 adults out of 300 adults were smokers, then you would do the p hat as 100 over 300. Okay, and that's how you would find the p hat. But in this case, they already told you what the percent was, so we're going to use that. So 0.20, and then they mentioned that the actual p was from the hypothesis, the claim, which is 0.24. So we have 0.20 minus 0.24 over the square root of, now we know that p is 0.24. So the q in this case is, remember, it's 1 minus p. So it's 1 minus the probability of success, or the population proportion. And n is 300 people that were surveyed. And that was from our sample size, and we double check that. Yep, 300 adults. All right, so now we're going to go ahead and calculate this. We know that the numerator is going to be negative 0.04. Be very careful with the denominator. So for the denominator, I would suggest doing the denominator first, and then saving that number, and then dividing them, rather than doing them all at once, just in case. Although I tend to do it at the same time because I know how to operate the calculator in such a fashion. All right, so the test statistic is about negative 1.62. All right, so we got our z-test, so that's our z-score. We're going to label that on our curve. So the z-score that we calculated is around here. So this right here is our z-critical. And then up here, it's going to be our z-test, which is negative 1.62. All right, so notice that is outside of the red region. So it's outside of the rejection region. So because of that, we're not going to reject, we're going to fail to reject the null hypothesis here. All right, so since it's outside, we fail to reject. So what do we conclude? So we conclude that there is not enough evidence at the 1% level of significance. And now we know that according to our first step, the claim actually belongs to our null hypothesis, so we're going to be using the word reject here. If it belonged to the H1, we would use the word support. So there is not enough evidence to actually reject the claim that, and then we're going to go ahead and write out the claim. The proportion of US adults that smoke is, and I believe it was 24%. I will double check that though. At least 24%. So it was at least 24%. All right, and so we're going to finish this off with the final example. So the EPA claims that more than 70% of US consumers want GMO labeling on all food. We want to test this claim. We find that in a random sample of 250 US consumers, 85% want GMO labeling on food. Is there enough evidence to support the EPA's claim at a 5% level of significance? Okay, so here, let's write our claim first. So let's label this stuff. So we have they claim that it's more than 70%. So this is our P. We find that in a random sample of 250, that's N, 85%, that's my P hat. One GMO labeling on food. Is there enough evidence to support? So we got our alpha of 5%. So that's our important stuff. So in this case, the EPA's claim is that it's more than 70%, which is 0.70. So that's a statement of inequality. Therefore, what we're going to do, we're going to put that as our alternative H1. And then we're going to reverse it. We're going to do the opposite of that, the complement, which is going to be less than or equal to. All right, and that's my H sub 0, my null hypothesis. Now my alpha, we said was 0.5%, 0.05. Now, based off of our alternative hypothesis, that's pointing in the right direction. It's greater than 0.70, so that's going to be a right-tailed test. All right, so that means it's going to be a positive critical value. So now when we do our area, remember our area for our right-tailed test is going to be 1 minus alpha when we're talking about a z distribution. So it's 1 minus alpha, and alpha is 0.05. So it's going to be 1 minus that is 0.95. So we're looking for an area of 0.9500. All right, so we're going to look that up on the z table. .9500. The closest area to that are these two areas. You can choose any one of them. I will go ahead and choose the 0.9495, and that will give you about 1.6, about 1.64. Again, technically the test statistic here is 1.645 between the 1.64 and then 1.65, but that's fine. You don't have to be as exact for this. So 1.64 would suffice. All right, so going back to our graph, we have 1.64 as my z crit. And then we'll shade the area on the right side for the right-tailed test. All right, and that area is worth 0.05. So that alpha is 0.05, the 5% that we chose. All right, so now what we're going to do is, well, we're going to label this first. That's positive 1.64. Now we're going to calculate our z-test. So remember the same formula, p hat minus p over square root pq over n. So the p hat they told us in this problem, so it's going back to the original problem here. 70% of US consumers want GMO labeling on all food. That was p. And then 85%, that's our p hat. Okay, so 0.85, and then n is 250. Okay, so we got 0.85 minus what was the other number? 0.70 over square root. We have 0.70 times 1 minus 0.70, that's how you find Q, divided by, and I believe it was 350 US consumers. Let me double check that. 250. So let's change that. So 250, and then we're going to go ahead and do the calculation. Again, being careful of the denominator and the numerator. All right, so when I calculate this, I get approximately 5.18. Okay, so that's my z-test. So that is a large z-score, relatively speaking. So if you look at here, this is 4, this is 5. So you're all the way on this right side of the curve. So we got a z-test of 5.18, and that's all the way on the right part of the tail, right? So this entire region is the rejection region. So it is actually inside that rejection region, which means that what we're going to do is we're going to reject because we're inside the red region. So inside the red means reject. All right, so we are going to go ahead and reject the H sub 0, or the null hypothesis. And then that means we have enough evidence. So we're going to say there is enough evidence at the 5% level of significance to, now our claim, going back to our step 1, our claim belongs to our null hypothesis, just like it did before. So therefore we're going to say, yeah, so we're going to use the word reject here. Oh, I'm sorry, I'm looking at the wrong one. So our claim belongs to not our null hypothesis, our claim belongs to our alternative. I was looking at the first problem. So the claim in the second problem belongs to the alternative, which means we're going to use the word support. Okay, so there is enough evidence at the 5% level to support the claim that, and then we'll write our claim down. And then so it says it was the EPA's claim that the proportion of US consumers who want GMO labeling is more than 70%. All right, that is it, guys. I hope you learned something from this video. And as always, I will see you in the next one.